Product of array except self. Want to stand out in any technical interview? Product of array except self is a must-know pattern mastery 100 problem that appears again and again in Phong interviews. Many candidates get tripped up by constraints, like not using division and achieving ON time. If you can solve this one efficiently, you're proving you can handle real-world algorithmic challenges under pressure. Ready to see the trick that interviewers love? Let's go. Let's break down the challenge. You're given an array of numbers. For each position, return the product of all other numbers, except the one at that position. The twist: you can't use division, and you need to do it in ON time. The output is a new array where each index holds this special product. Let's assess our options. A brute force approach would calculate the product for each index separately, ON squared time. Not efficient. Using division would make it ON, but the problem says no division. So how do we do it? The trick is to use prefix products and suffix products. Prefix: product of all numbers to the left of each index. Suffix: product of all numbers to the right of each index. By multiplying the prefix and suffix at each index, we get our answer without ever dividing or missing a value. Here's our structure. Create an output array, initialize to ones. Pass left to right. For each index, multiply the product of all numbers to the left, prefix, updating the output. Pass right to left. For each index, multiply the product of all numbers to the right, suffix, updating the output again. The result is the product of everything except self at every index.
Let's try to implement it using solution 1. We start by creating a class named solution, just a container that holds our method. This defines our function product except self, which takes in a list of numbers. Our task is to build a new list where each position contains the product of all numbers except the one at that position. Here we store the length of the list in n. This keeps our code clean and avoids repeatedly calling len nums. We create a list called prefix, filled with ones. This list will store products of all numbers before each index. Starting with ones is important because multiplying by 1 doesn't change the result. Similarly, we create a suffix list, also filled with ones. This list will store products of all numbers after each index. We begin a loop to fill the prefix products. We start at index 1 because the first prefix value stays 1. There are no numbers before index 0. This loop runs in ON time. Each prefix value is built by multiplying the previous prefix product by the previous number in the list. It's like walking forward and constantly keeping track of everything you've multiplied so far. Now we fill the suffix products by looping backward. We start from the second to last index and go all the way to 0. This loop also takes ON time. Each suffix value is created by multiplying the next suffix product with the next number in the list. Think of it as tracking everything to the right of each position. We create a result list filled with ones. This will hold the final answer. Now we go through every index to combine prefix and suffix values. This final loop is also ON. For each position, we multiply the product of everything to the left, prefix, with the product of everything to the right, suffix. That gives us exactly what the problem asks for. Finally, we return the completed result list, which contains the product of all other numbers for each index. And that's how this algorithm works. It first builds separate prefix and suffix product lists, then combines them to create the final result without ever using division. Efficient, simple, and elegant. Check. Let's walk through this test case to confirm the product of array except self logic works correctly. Here's the input. Nums equals 1, 2, 3, 4. Each number represents a position in the array. And for every index we want to compute the product of all other elements except the one at that index. Our solution does this by building prefix products, left side, and suffix products, right side, then multiplying them together for each position. Here's the breakdown. For index 0, product of 2, 3, 4. 2 times 3 times 4 equals 24. For index 1, product of 1, 3, 4. 1 times 3 times 4 equals 12. For index 2, product of 1, 2, 4. 1 times 2 times 4 equals 8. For index 3, product of 1, 2, 3. 1 times 2 times 3 equals 6. This gives us the final output, 24, 12, 8, 6. The output matches the expected 24, 12, 8, 6, confirming the algorithm is performing the prefix-suffix multiplication exactly as intended. Now let's try another implementation approach using solution 2. We begin by defining a class called solution. This is simply the container that will hold our function. Inside it, we define the function called product except self. This function takes in a list of numbers and returns a new list where each position contains the product of all the other numbers except the one at that position. We store the length of the list in a variable named n for convenience. Next, we set up a result list filled with ones. Starting with ones ensures multiplication works cleanly as we build up the answer. We then make our first pass through the list, starting from index 1. In this forward pass, we build what are called prefix products, the product of everything to the left of each position. At each step, we multiply the value from the previous position in the result list with the number directly to the left in the input list. This gives us a running product of all left side elements. Before starting the second pass, we create a variable called suffix and set it to 1. This will hold the running product of elements on the right side of each index. Next, we loop backward through the list, starting from the last index and moving to the first. In this backward pass, we multiply the existing prefix product stored in the result list with the current suffix value. Prefix times suffix gives the product of all elements except the current one. We then update the suffix by multiplying it with the current number, preparing it for the next step to the left. After both passes finish, we return the result list. Each position now contains exactly what the problem asks for. In summary, this algorithm builds prefix products in a forward pass, builds suffix products in a backward pass, and combines both without ever using division. It is efficient, clean, and elegant. Check. Now let's confirm the behavior of this solution using a more challenging input that includes negative numbers and a 0. The input is -1, 1, 0, -3, 3. Zeros dramatically affect multiplication, so this is an excellent test. The goal is to compute, for each index, the product of all the other values except the one at that index. For index 0, the values are 1, 0, -3, and 3. Because there is a 0, the product becomes 0. For index 1, the values are -1, 0, -3, and 3. Again there is a 0, so the product is 0. For index 2, the values are -1, 1, -3, and 3. There is no 0 here. Multiplying them gives 9. For index 3, the values are -1, 1, 0, and 3. There is a 0, so the product is 0. For index 4, the values are -1, 1, 0, and -3. Again there is a 0, so the product is 0. This gives us the final output, 0, 0, 9, 0, 0. The output matches the expected answer, confirming the algorithm handles zeros and mixed signs perfectly.
Let's have a quick recap. Breakdown recap. So, to wrap this one up, the challenge was to build a new array where each position holds the product of all numbers except itself, without using division. It's a clean, logical problem that tests both array manipulation and optimization skills. Assess recap. We compared approaches and saw that a brute force method would take O(n)² time, far too slow. Division could simplify things, but that's not allowed. The real trick was realizing we could compute everything using prefix and suffix products, one pass from the left, one from the right, all in linear time. Structure recap. The plan was simple but elegant. First, make an array of ones. Then, do 2 sweeps, one left to right to store the prefix products, and another right to left to multiply in the suffix products. When both passes are done, each position has exactly the product of every number except itself. Implement recap. In code, this came together beautifully. The logic flowed through 2 clean loops, no division, no nested iterations, and constant extra space. It's efficient, neat, and easy to understand once you see it in action. Check recap. When we ran the example, 1, 2, 3, 4, the result, 24, 12, 8, 6, confirmed everything worked perfectly. All test cases passed, validating both the logic and efficiency. The key takeaway? You don't always need complex data structures, just clever passes and careful thinking. This problem is a reminder that mastering prefix and suffix patterns unlocks a ton of real-world coding efficiency.